Welcome to Spring LIB.
In this exercise, we're going to need the concepts of circular motion and friction force. So I'm going to briefly review these concepts before we dive into the exercise. So first, let's talk about circular motion. Remember that the centripetal acceleration, that is, the acceleration that points towards the center of a circular orbit performed by a certain particle, is equal to v squared divided by r. And this particle has an acceleration even if its speed is constant. That is, if the magnitude of its velocity is constant, but the velocity itself is moving, is changing in direction, then there is an acceleration that is given by this formula. Also, we have to review the concept of friction force, more specifically, the concept of static friction force. So basically, the static friction force happens when an object is at rest relative to a surface, and there is a certain friction between the surface and the object. And this friction varies from the value of 0 to a value of μs times the normal, where the normal is the force that the surface exerts on the object. Okay, and if the force that acts upon the object is greater than the friction force, the static friction force, then the object starts to move. And then what comes into play is the kinetic friction force, where we have that the kinetic friction force is equal to the coefficient of kinetic friction, mu k, times the normal. So now we are ready to dive into the exercise. So what we have in the exercise is a spool that has a mass of 2 kilograms that is loosely attached to a rod that is inclined, as shown here in the figure. And the spool is at a distance from point A of 0.25 meters. And the rod is such that the triangle formed by the rod and the horizontal line, this line here, is similar to a triangle that has a hypotenuse of 5 and the legs of 3 and 4 as shown here. And the rod starts to rotate such that the spool S starts to rotate. And the coefficient of static friction between the rod and the spool is equal to 0.2. Given this information, our goal is to find what is the maximum constant speed v that the spool can have so that it will not slip up the rod. Okay, so in order to solve this, what we need is to draw a force diagram on the spool. So this here is a spool. We have the normal force that the rod exerts on the spool. We also have the friction force, the static friction force, and so we do not want the spool to slip. And since we don't want it to slip up, then let's consider that the spool is on the imminence of slipping up, so the friction force is pointing downwards. We also have the gravitational force, and that's it. These are all the forces we have. And I'm going to set a coordinate system such that the y-axis points upwards and the x-axis points to the left. So let's write the forces, let's write Newton's second law in both the x and y coordinates. So in order to do that, I'm going to decompose the normal force and the friction force on their y and x components. So here we have theta, and here we have theta. Now notice that theta is the angle that the rod does with the horizontal. And since we know that this triangle here is similar to a triangle that has a hypotenuse 5 and legs 3 and 4, then the sine of theta is equal to 3/5, and the cosine of theta is equal to 4/5. Okay. So in the y-coordinate, we have n times the cosine of theta minus ff times the sine of theta minus mg is equal to 0, since the spool is not moving in the y direction. And in the x direction, we have n times the sine of theta plus the frictional force times the cosine of theta. And this is equal to, according to Newton's second law, the mass times the acceleration. Now the spool moves in a circular motion, so the acceleration is v squared over r, as I said before. Now, what exactly is r here? Notice that the distance between point A, through which the axis of rotation, this axis here, passes, and the spool, the distance between these 2 points, is 0.25 meters. But this is not exactly the radius of the orbit, since the radius is this distance here. So what we can find in order to, what we can do in order to find this distance is use Pythagoras' theorem, or better, we can use the triangle that was given to us. So this here is theta. So we have that r is equal to 0.25 times the cosine of theta. So it's 0.25 times 4/5, so that's 0.2 meters. So that's r. Okay. Now notice that we want to find the maximum possible value of the speed v, and this means finding the maximum possible value of the frictional force F. And as I said before, the maximum value of the static friction force is the coefficient of static friction times the normal force. Okay, so I'm gonna consider that the frictional force is maximum. So I'm gonna substitute this into the y component. So we have n cosine of theta minus mu s and sine of theta is equal to mg. Okay, this is the equation for the y-coordinate in this extreme situation. And the equation for the x-coordinate is n times sine of theta plus mu s and cosine of theta. And this is mv squared over r. Okay. Remember that our goal is to find v. So first, we have to notice that there are two unknowns. We don't know what n is, the normal force, and we don't know what v is. And it's going to be impossible to find v if we don't know what n is first. So let's do that. I'm going to take the y equation, the equation for the y-coordinate, and isolate n. So we have that n is equal to mg divided by cosine of theta minus mu s sine of theta. And now I'm going to take this and substitute it into the equation for the x-coordinate. So we have that the equation can be written as n times the sine of theta plus mu s cosine of theta times r divided by m is equal to v squared. So instead of writing v squared, I'm just going to take the square root on the other side of the equation. And now I can substitute the n. So n is mg. and then divided by cosine of theta. I'm sorry, I'm just multiplying by what I need to multiply in the numerator first, and then I'm going to divide by the denominator of the normal force. So that's cosine of theta minus mu s sine of theta. Okay. And then we have to multiply by r and divide it by m. So I'm going to just take the m out of here. And this is equal to v. Now all we need to do is to substitute the numbers. So g is 9.8 meters per second squared. R, the radius, is 0.2 meters, as I said before. The sine of theta is 3/5. Mu s is 0.2. Cosine of theta is 5/5. Then we have 4/5 minus 0.2 times 3/5. And we obtain that v is equal to 1.48 meters per second, which is the answer to our exercise. This is the maximum value that a spool can have so that it does not slip up the rod.